pronounced reorganization of wintertime North Atlantic atmospheric circulation regimes. So please go ahead.
Yeah, thank you very much, Carsten. Also, thank you very much for the opportunity to present some of my recent work here. I'm sorry for this rather lengthy title. I mean, what I'm presenting today is mainly work done by my PhD student, Sue Smith, who's going to finish this summer. And that's also in collaboration with Vincent Rayan, who's at the Barcelona Supercomputer Center, and Terry O'Kane from Australia, CSIRO. So what I'm going to talk about is basically atmospheric regime state, and there is this, which I also going to explain in more detail during the introduction of my talk, this question whether they actually might change due to global warming. So I have to use the mouse to go forward. Here, this animation is just to give you some flavor of what's actually going on, climate or atmospheric variability in the atmosphere, or not kind of some structure, are there actually persistent circulation systems, which actually might improve long-range predictability. If you look over long periods of time at weather maps, then you actually see that there are also so-called clocking situations, something displayed here on the left side, which is a so-called omega clocking. And clocking basically means, if you look here more at the climatology, at the right-hand side, so we would have more the zonal flow circulation structure, where the cyclone could actually travel unperturbed across the North Atlantic and then make landfall over the European continent. Blocking basically means that the typical flow is blocked. So cyclones basically have to first move forward before they basically can then come back towards Europe.
Christian,
and those blocking, yeah.
Sorry, Christian, 20 years ago, we would have called this the North Atlantic Oscillation. What's the difference to that?
I will come to this. I mean, that's the North Atlantic Oscillation is the big part of this. So let's just give me a moment to explain this. So that's
okay.
So the question is, how will this actually might change? Do we have more of those blocking situations or not in the future? That's kind of where I want to get to. One of the simplest approaches to this was kind of looking at a reduced order model, where you can actually also look at steady state. And that was pioneered by Charney and DeVore. They looked at the barotropic channel model, did the spectral extension, and basically reduced it only to 6 spectral modes. So it's very coarsely resolved with topography, which is here displayed by this kind of gray shading. And you can see here we get 2 equilibrium states. One more the zonal flow, and one the more blocked flow. You can also see this as the 2 phases of the NAO, which I also discuss here, with Carsten already mentioned. That's what's called the North Atlantic Oscillation, where the negative phase would correspond to this blocked situation. And there we have also then large impacts on surface conditions over Europe. So in the Mediterranean might be warmer and better during the winter time, whereas in Hamburg and Scandinavia might be cold and dry. Whereas if we have the so-called positive phase, the more zonal situation, then it might be warmer and wetter, Scandinavia, Hamburg, but cool and dry in the Mediterranean. So how do we actually identify those regime states in data? So for this, we use so-called empirical orthogonal function analysis. That's a statistical technique to basically decompose the data set into basis functions. And we use this to actually reduce the the dimensionality of the problem. If we would just look at the analysis data sets, grid points, then we just have too many data to actually try to identify the structure in the data. So we try to reduce the dimensionality. EOS are one approach. And basically there we kind of look for patterns which explain the most variance. So that would be the leading EOS. So in this two-dimensional example here, where we have, say, our observed data, the data cloud, and then we basically look for the axis where we have the most variation. That would be then basically the direction of EOF1. And then the following EOF would then be orthogonal to this. But of course, also very strong constraint on the dynamics, if you want to explain this. And then one could also go to higher dimensions, UF3, 4, 5, and so on. And they all need to be orthogonal to each other. So now if we do this, then we can basically compute EOS by looking at the eigenvectors of the covariance matrix, which we can compute, say, from reanalysis data. Then we identify the first two leading EOS, and then we can look at the phase space spanned by the, say, leading EOF here. If you just look at the northern hemisphere, EOF1 on this axis, EOF2 on this axis, we look at the joint PDF here, those isolines here, and we can see here that we kind of have some areas where we have somewhat increased probability density. And those areas can then be associated with those regime states, for example, the NAO, or in the North Pacific region, the Pacific North America pattern, which has the kind of a center of activity here in the North Pacific, and then kind of arches here over North America. So the idea is by identifying those states in phase space that we kind of have either recurrent states, so basically that the phase space trajectory of the weather basically goes to those locations very often, or that they actually are quite persistent, that they actually stay there very often. Both situations actually would also increase predictability. So that's, of course, if you're interested in long-range predictability, business forecast also, that's, of course, what we want. And the idea is also that there would be preferred transitions between those regime states, which we can then also later actually determine by looking at, say, Markov transition matrices. So here already in Kimoto-Gill, 1993, they came up here with this schematic where we have those regime states where the weather or the circulation state persists or occurs very often, and then we have those transitions where we go to the next one and so on. There might also be quasi-cycles or so. So, and the question is how this might actually then change in the future. There's, of course, not only the North Atlantic Oscillation, which we already discussed, but also, say, in the Atlantic region, we have the East Atlantic pattern or the East Atlantic Western Russia pattern, Scandinavia pattern, which is related also to blocking polar ovation pattern and many of those patterns. So if you also go more towards the weather forecasting, they have even more of those preferred weather situations or gross weather lagen, 30 or 40. So it's now the question how to identify them and how they actually might change in the future. Do we have more of those states or less? But maybe before I go there, a few more words about the impact. Why are we actually so interested in the North Atlantic Oscillation here or the East Atlantic Western Russia pattern, East Atlantic pattern? If we just look, if we are, say, in the positive phase of linear or negative, and look at the correlation coefficient between those circulation indices and some weather or extreme indices like accumulated precipitation here, RR, consecutive wet days or consecutive dry days, which of course would have impact, say, for agriculture also, then we see here also strong correlation. So if we can predict the state of the NAO a few weeks or months in advance, then we can kind of, at least in a probabilistic sense, also say something about precipitation amount and maybe dry spells or so. Also, it's of course also very much related to wind speeds or storm systems. And we are, of course, nowadays also very much concerned about renewable energy. And here the study by Graham that basically also look at different North Atlantic regime states and how they actually impact on a European-wide scale wind energy potential. So depending on the actual regime state we are in, then certain regions might have more wind, others less, but overall, they find actually there should be always enough wind. So that's of course good for European renewable energy, but maybe more towards this talk will actually then be about kind of how climate change might affect those regime states. There is this study by Corti et al. From 1999, who first kind of discussed this. So they looked, like Himoto and Gale, at the joint PDF of UF1, UF2 over the period 1949, 1994. And they find here evidence of those 4 regime states. And then they also checked if with or without ENSO, whether there is actually much of a change. But if they remove ENSO, kind of looks quite similar. We still have those 4 states. Maybe they moved a little bit in the phase space. But then the more important aspect is down here. So then they basically put or split the data set into half, 49 to 71 and 71 to 94. And here we can see that basically they only see kind of 2 pronounced peaks. And then they also shift here in the latter period. So in this paper, they kind of claim that we can already see the impact of or the fingerprint of global warming in those circulation regimes, that they might have a strong impact on the spatial structure. Basically, if we move from here to here, that's of course would also change the spatial structure and maybe also the frequency of currents, so to say. So a couple of years later, there was a much more statistical-based study by David Stevenson et al. They basically say with the amount of data we have, we basically can't really find statistical evidence for something like a multimodal distribution. So what we have here, basically, if we would have only 1 peak, so we would have a unimodal distribution, so we have 4 peaks. That's what we call a multimodal distribution. So that's actually, you would need a huge amount of data to actually say something, whether you actually have 2 or more peaks in your distribution and whether they actually might change. So basically, they basically say all you can do is try to reject the single regime null hypothesis. But they basically, if they look at the data they had available back then, they actually could not basically reject the null hypothesis of just multi or unimodal distribution. So now we have much more climate model data, also large ensemble, which we're gonna use to actually try to resolve this question. But first, are there actually changes in the regime structure, and are they also significant? So in this study, we kind of try to address those research questions. How does climate warming influence structure and frequency of North Atlantic regimes and also North Atlantic variability? Then does the externally forced climate change signal alters also the internally generated regime behavior? That's actually something we actually can do with those large ensemble simulations. and how does external forcing reorganize the circulation? Basically, how will those regime states change and how will they affect the annual phase behavior? I already mentioned here we use a large ensemble. That's something we at our institute here at the Center for Climate Physics at Pusan National University carried out in collaboration with the National Center of Atmospheric Research in the US. So we use the community Earth system model version 2, large ensemble. So we ran the same setup, the same forcing. We use SSP3 7.0 scenario 100 times, starting from different initial conditions for the period 1850 to 2100. So this gives us now a really good and large data set to also look at this question about changes in regime, because then we can also be quite confident that what we see actually is also statistically significant. So if we would look at just the ensemble mean, that's what would be the forced response. But if we now take the forced response ensemble mean, subtract this from the full flow fields of each ensemble member, then we can get some estimate of the internal variability. So here in this study, on one hand, we look at the full flow field. So that's basically, if we look at reanalysis data, there we can not really distinguish what the component is of the change in the circulation due to global warming and what would be, say, just internal variability. Here in the large ensemble, we actually can do that. So we can do that. Kind of, this would be more or for fair comparison with reanalysis data. And here we can basically see which of the changes are due to global warming and also does global warming kind of affect the internal variability. So that's something we can now do with a large ensemble. How do we identify regime state? So before I showed you just the phase space diagram, the joint PDF, and then we can see there might be multiple peaks. There are lots of studies who use more clustering methods. One of them, which we use here, is the Gaussian mixture model. That's a statistical model. So we have the observed PDF, and now we kind of try to approximate or represent this observed PDF by a combination of multiple Gaussian distributions, and then the centroids of those Gaussians, that would be the regime state. So each Gaussian has its own mean and variance. So the mean typically would be what we can also call the centroid, say the center location of the regime state in phase space. And of course, also the range, so characterized by the range. So, and maybe it's easier to understand this here with two examples. That's just
Christian.
Yes.
Christian, previously you said it's very difficult to say if it's a multimodal distribution or a single mode, and now you come with many Gaussian peaks, right? How does that fit together?
The question is, of course, then now how do we decide how many Gaussians we actually try to use? What Stevenson's et al. Here say, it's basically you need a lot of data. And the large ensemble, 100 ensemble members, then we have long time series. That gives us, of course, much more data than basically they had available 20 years ago. So now we can actually try to address this question, which was previously not really possible because they had much less data available, especially if you look at observed data or reanalysis data.
And how do you decide how many modes you take?
We use them. I will also then discuss this. We use the information criterion. So so basically it's a compromise between the the quality of the model fit. Of course, the more Gaussians you would use, the better you can actually fit the observed PDF or the model PDF, but then you might overfit. And this information criterion basically provides some kind of compromise. But I mean, that's still kind of a critical issue. I mean, there is, of course, no very strong argument. I mean, there are lots of different methods you could use to decide how many regime states or Gaussians to use.
You could do this.
That's somewhat subjective.
You could do the significance test afterwards from Stevenson.
Yes, I mean, yes, I mean that we also then look at Hermomova. We also look whether we actually see this change in there. So I get to this
Okay.
shortly. So here, just we have this observed PDF with the gray bars, and basically we can basically represent this due to the two Gaussian components. Maybe one dimension is maybe quite straightforward, two-dimensional, or we can do this in much higher dimension. So we have here our data cloud, those dots here, and then here's probably if you would only see the dots without color, maybe not so obvious how you might actually organize those dots, but then we would have here the mean of the Gaussian, which we also call the centroids, and then basically here also the variance or the covariance, which also says something about the extent of the, or which points actually would belong to those regime states. Okay, maybe now getting to our model data first, some evaluation, how well the CSM large ensemble actually performs when it comes to stream function, which we're gonna look at, or to potential height fields and also surface temperature. So we can see here that the PDFs actually relatively well captured between era 5, CSM2 for the period 1940 to 2024. If you look at surface temperature, CSM tends to be a bit colder than era 5. Here we can also see here this dark line also here for stream function temperature. That's the era 5 data for the observation period here. And we also see here the blue or red line, that's then the CSM from 1860 to 2100. And you can, and that's also here for all 100 ensemble members. That's why you see this big blue plot or the red plot here. And you can also see here, it's maybe tends to be a little bit too cold, but probably good enough for our purposes here. So now we want to have a strong connections between circulation change, the stream function, and surface temperature. So instead of using empirical orthogonal functions, we actually do a single value decomposition, basically a joint analysis or decomposition of stream function temperature. So we basically compute the covariance matrix between stream function of the grid point fields and surface temperature to the eigenvalued eigenvector decomposition. Now we will basically get two orthogonal matrices, U and V. One corresponds to stream function, the other to surface temperature. And of course, we solve this diagonal matrix here. And the eigenvalues, they correspond to basically the explained variance of those joint patterns. So here we do this on the left side for the full flow fields, on the right side here, internal variability, where we subtracted the ensemble mean. And you can see here, so that's the first SV single value vector, and here the second. So you can see here kind of temperature deviation, and also if we would flip the sign, then kind of the SVD1 kind of would correspond very well between full flow field internal variability. So we capture probably in the full flow field quite a lot of the internal variability. But then here, SVD2, we see already more changes. So that might then be in either due to the orthogonality condition or maybe some impact of global warming. But that's basically, we take those vectors now basically as our phase space coordinates to look at them. So now we of course want to look at the impact of global warming. Where do we, and we decided to basically also have a kind of a time point where we basically have, say, where we claim that it appeared without much impact of global warming, and then once where it actually becomes more and more pronounced. So we look at those principal components of the single vectors, so which are displayed here for stream function and here for temperature. And then basically we look at a change point. So we do a statistical test. Where does actually the slope change? So in the first period, basically we have a very shallow slope, and then when would this actually increase? Because we expect with global warming, then of course change. So especially here, if we look at temperature, where we then see this very strong increase, say starting sometimes in 1980s, 1990s or so. And the earliest change point we can identify in the stream function, and because we want to say something about atmospheric regime, was in 1995. So basically that's the point we now use to basically look pre-1995 conditions and post. So if we then look here at ensemble mean stream function pre-1995, that's how it looks. And post-1995, kind of we see here kind of this change, say here in the sign. So first positive, then it gets here flu negative. So we kind of see already strong changes in the stream function and in the stream function anomalies here. Okay, now we have all those principal components, basically how the singular vectors evolve in time. So we can span here principal coordinate 1, coordinate 2, and then basically do the Gaussian mixture analysis, and we kind of find evidence for C. Say if we first focus here on the full flow fields. So now we do the spatial information criterion, as I already mentioned. That's just kind of looks at this compromise. How good is the model fit? How well do we actually fit with 4 Gaussian mixtures, the full PDF? But also tries to penalize model complexity. Model complexity would mean here more and more Gaussian mixtures. And if we do this, so basically we find here strong evidence for 4 regimes, pre-1995, also post-1995, for the full flow field. If we go to the internal variability, here we actually see also pre-1995 strong evidence for 4 flow fields, but then post-1995 evidence for only 3 flow fields. So while for the full flow field, say maybe including global warming, there is basically no evidence for reduction of the number of regime states, but for internal variability. So that's the interpretation we have for this here is basically the global warming, there is a direct response, but then also kind of affects the internal variability by reducing the number of those regime states. Then we also have here, yes?
Did you also do the significance test from Stevenson? If there's a significant...
We did this Thermonova, which I wanted to talk about now.
What? So,
we also now wanted to see whether we can actually distinguish between those different regime states, the locations, and whether they change. So that's what we can do with this test here, which is called Permanova. And we basically find statistically significant differences amongst those clusters, which with respect to the locations of the centroids or the mean states and the variances.
No, I mean,
So that's
if the decomposition into 4 modes is statistically significant, because in Stevens it was not, right? Even for 2 modes. And here you have 4 modes.
yes, but here we have much more data.
Yeah,
So
yeah.
it's of course much easier to find statistical significance.
Yeah, but did you do this test? That is the question.
Yes,
Okay, and it is significant.
yes.
Okay. But I
Okay.
could also add then 2 more. Would that still be significant?
You mean 6 states?
Yeah, or 10, whatever.
So here we find kind of evidence for 4 and tier 3.
Okay, and if
So
I would
6,
on the right, if I would add another one, would that be statistically significant? Or
no, that's kind of the 3-component model is much better.
okay, that is your evidence that you only have 3 modes in the post area.
Yes,
Okay.
of internal variability. In the full flow field, it would still be 4. So there is something then also, I mean, that's something we still don't fully understand, but there's kind of some indirect, or I don't know, some impact of global warming here, what we call the internal variability, that can still have this effect to change also internal variability.
Okay.
Okay. Okay, here now we have those 4 or 3 states. Now to discuss them a little bit and how the structure changes. Here I first focus what we call the most frequent regime state, how this actually might change. Again, here on this side, full flow field, on this side, internal variability, P90, 95 here on top and post 90, 95 on bottom. So you can already, and here stream function and surface temperature. So you can already see here the most frequent regime state kind of has some changes. I mean, here this negative area extends now or moves kind of much further forward. And also here, maybe there is this positive area of stream function extending much further into Europe, which might then also impact, say, weather, surface weather conditions over Europe. Also here for surface temperature, maybe the most pronounced change is here we still had something like a positive, negative, positive pattern over the North Central America. Now it's kind of only warm, but we also see here this, I think also well known, I think also in CSM, the whole so-called warming hole in the North Atlantic Ocean. This also gets much more pronounced. That's also kind of something very pronounced in CSM2. So that's here. Internal variability, you see also kind of change of the sign here, and maybe before stream function anomalies were much stronger, here somewhat weakening. Also here, surface temperature kind of from change for the most frequent states, from maybe more the seesaw between cold America, warm Europe, to basically more warm. Or if we are in this state now, in this most frequent state, it's more warm in the US, where it's much or more relatively colder than in Europe, so to say. Now we have those cluster states. Now we can, of course, also look something in how persistent they are, does the persistent change, and also the transition. If we then basically are, say, in one cluster state, how likely is it that we go into a different one, and how does this change due to global warming? So we have here 4 cluster states, pre and post. So the coding here, the leading one here is always, it's basically pre-1995 cluster 1, let's focus on this. And so that would then change to cluster 2.1. 2 basically indicates we are post-95. Maybe, so here we have the transition matrix. If we focus first on the most persistent state, pre to post-1995, we actually see it becomes more persistent. Also, in pre-1995, we have maybe stronger probabilities to go from one state to the next here. Also here with the roads, whether we go from 1.1 to 1.2 or 1.2 to 1.1. So the probabilities here, they kind of weakened post 1995. So that might indicate that whereas here we kind of have a strong quasi cycle also, or preferred transitions between regime states, they seem to become much weaker. So that might indicate for long-term predictability that actually that might become much harder, because that what maybe gave us predictive skill in the past might become now much weaker. So how does this now relate also to the North Atlantic Oscillation? Because that's something many people know very well. So again, here full flow field, internal variability flow field for the NAO pattern. And here we define the NAO pattern now as the leading EOF of surface pressure to be consistent with many previous studies. So now we can look here again at the temporal evolution of this and compare this here to ensemble mean. And here we see kind of, or the forced response, that is kind of this long-term trend towards the positive phase, which we also kind of see in the actually observations and many other studies. So how is now the NAO? We can of course now see or imagine NAO kind of a superposition of some of those regime states. How does, if we kind of keep this NAO pattern fixed, how does this now relate to those changes in those regime states? So now kind of we try to decompose the NAO. Here we have the index. How often do they correspond to those different cluster states? And here we kind of see full flow field, again, internal variability, that there are 2 flow fields which are kind of have very high overlap for the positive phase, or then different states for the negative phase. Also and this kind of also kind of weakens, and it also kind of seems to be spread among more of those cluster states as we define them in our study. And something similar here for the internal variability. Of course, here we also have the reduction in the number of regime states. That also, of course, means that basically, especially here, this most frequent regime state then becomes much more prominent.
Christian, can I annoy you
Yes.
again with significance? Can you say that this change is significant? Say if you reorganize your time series and pick random years and also organize in 2 different phases and do this 1,000 times, could you say that this change is then significant compared to some hypothesis?
That would be something like a bootstrap method, and
Yeah,
I
something
think
like
that
this.
should allow us to give, that should be a significant step.
Yeah, but if you would do this or something similar, more fancy, would that show that it's significant, or?
We haven't done this except this in particular not here. But that would be, maybe that would be a good idea.
Okay, so then so far you cannot say that this is a significant change.
Yes
or no?
Here we have basically the changes in the regime structures that's kind of statistically significant. Now we basically kind of just look how this kind of relates to the NAO. How our regime states, those changes are statistically significant, how this kind of can be related to the NAO, because many people are interested in the NAO. That's kind of what we want to do here.
Okay, so by implication, if the previous analysis was significant, you can also say that this is significant. Okay.
It's likely, yeah.
But then my question would be, why is the previous one significant? But maybe we can discuss this later.
Yeah. Okay, then here if we look at some more statistics, say the median value of the NAO index pre and post, here we kind of see a strong change from 0.08 to 0.2, also kind of significant change in the median, and also the interquartile range kind of changes, gets more towards kind of the whole distribution, as I already showed in before, kind of moves towards more positive values. Whereas here internal variability, we see kind of less of much of a change. There is maybe even more reduction in variability, which we also I can show you probably in the next 1 or 2 slides. So if we look here, basically average number of months per realization where we are in the negative NEO phase, kind of here we see this decrease, but then 2081, we kind of see a rebound. That's also something we are not very sure. So if we look here, basically negative phase, positive phase, they of course kind of move in opposite directions. So we have this long-term increase in the positive phase, but then towards 2080, 90 or so, then kind of this reduction, which is, we still have to better understand. So then, so the NAO is very strongly related to the solar wind or the westerlies across the North Atlantic region. And how does this kind of change also in relation to those regime states? So here we have pre-95, post-95, and that's always for the full flow field here, all of them. And we can see here, we kind of, if we compare pre with post, kind of typically kind of an intensification of the solar wind and maybe also more move towards Europe. Also here in the most frequent one, we also have here maybe the small polar jet and the subtropical jet, and the subtropical jet kind of weakens here, but then maybe in this cluster state here, then maybe this takes over more of the subtropical jet structure. Okay, now weakening of NAO variants, basically for both full field and the internal variability. I think that's also something of interest, so that the variant, I mean, that's also been kind of how we gonna have implications for long range forecasting, so that basically we might stay in a more confined range of NAO values. And so that's kind of, so starting here in CSM2, that would be kind of year 2025 again. We just look here at the variance across the ensemble members. Then we do a change point analysis. Basically, this slope gonna change. And here, more or less for both full field and internal variability, it happens at about year 2025 with statistical significance. Okay, to summarize my presentation, So in our study, we demonstrate the role of external forcing in changing or modulating atmospheric flow patterns of the North Atlantic region under global warming. We find there is kind of a complex interplay between global warming and the internal variability of the system. And global warming does not alter the number of those regime states in the full flow field. So what they, the Corti et al. Study, but it kind of changes the spatial characteristics. So in the full flow field, as in Corti et al., I don't really find this change in number of regime states, only for the internal variability. And we kind of projected the NAO gonna still consist of this shift towards more positive phases, but also has this reduction of the variability, but then also towards the end of the 21st century, it actually might actually go back to less positive phases statistically. So if you're interested in this, that was just published 2 or 3 months ago in Communications Earth Environment. And I'm also happy to answer any questions.
Yeah, thank you very much, Christian.